Hi folks, so the questions we have in front of us here today, guys, are the Leaving Cert Section A higher level from 2020. So what I'm going to do is I'll be completing all 4 questions, but starting off by focusing on this one here up in the top left. On the top left, question A1, which we can see here is based on the topic of axonometric projection. So I'm just going to zoom into that there now. Right folks, so we can see here in this question, it says question A1, the image below shows a paperweight, so we can see the image here, and obviously we've kind of got a graphic of it here as well. It consists of a cube and a square prism which intersect each other. Okay, so we can see obviously the cube here, and it is intersecting of this square-based prism here as well. And the drawing shows an incomplete diametric projection of the paperweight. A pictorial view is also shown. Part A. Complete the diametric projection of the paperweight, and part B, determine and indicate in degrees the true angle between the surface ABCD and the horizontal plane. Okay, so we'll start off by tackling part A first. So looking at part A, we can see they've kind of given us here what would be seen maybe as an elevation and an end elevation. Generally the plan will be down here, but for axonometric you can often complete these by just doing the 2 views. And what we have to do is we have to complete the axonometric view of it down here. We're also given the diametric plane here. Diametric meaning 2. Okay, the 2 angles. We've got 2 angles here, this little green plane. And we've got 2 angles in here that are the same. So you've isometric, diametric and trimetric. Iso is where they're all the same, diametric is where you've 2, and then trimetric is where none of them are the same. So what we have to do is complete this here anyway. So you can see here on the side view here, or the end elevation, which is otherwise what it would be known as, we can see the surface A, B, C and D, okay, which is a square surface, kind of like this one over here. If you imagine, I'm just going to label them there. So if A is at the top, we might have A up here, and then it obviously comes down to B, C and D and B. So this will be B here, yeah, B and C down at the bottom, then D over here, and we can see C connects to H, which is on the ground. So at this point right in here is our H, and then this is our G back here. And then obviously we have E and F. So A connects to E, and then B connects to F. So just kind of using the graphic here to be able to help me, and obviously we can see then F connects down to G. Okay, so that's just kind of helping us out on what we're going to have to complete it. So you can see here already in the axonometric view, they've already given us the surface A, B, C, D. So what I'm going to now find is, just thinking, I've been given A, B, C, D. I want to be able to complete this, so I'm going to look for E and F next. Okay, so I'm going to use what they've already given me there. So they've given me the angle I need to project back at. So just a bit of sliding set squares there. So if I want to find E, E is going to be back here. Just make sure my pen is working there. E is going to be back there somewhere, and likewise with F. Okay, and same principle applies over here. Bit of sliding set squares. So to find E, follow E down from this view to match it up with this one. There's E there, and likewise with F. So you can see there, I'm going to have to bring down F a little bit further on this one. So there we have it. There is my E there, and there is my F. Okay, so to connect all of those up, A connects to E, likewise B will connect to F. You'd imagine they should be parallel. Just check. Just in the view, it probably appears parallel. A little bit off of that one. So there we have it. Okay. So there's E to F. Pull it over a little bit. Accuracy is a little bit out there. Right, so we can see here we've got the 2 faces. So we have the face A, B, C, D, and now we've got the face A, B, F and E, or A, E, F, B, however you want to call it. And at this point now, I want to find where F hits G G obviously connects onto H and H to C. So there's a face here as well on the bottom. So we've got the face B, C, H, G and F. So we want to find those faces. So exact same principles again. We're going to locate our points using the exact same method. Just build it up slowly, work your way around the object. So for H, it's going to be somewhere along there. And likewise with F. Obviously you'll be using pencils on today. And then same principles apply from the opposite side. So let's find H. So H is down along there. And let's find G now. G is there. So once again, just level those. So I've got G here, and then H, just to be able to find him exactly. It's here. And heavy those in. So C connects to H. I know H, as you can see over here, connects over to G. So that's basically where the cube is intersecting into the square base prism. And now that is our cube as it has intersected into the prism. What we have to actually is complete the prism portion of it. Okay, so I'm going to find the top surface first, because that's the surface I'll see kind of based on the angle that I'm looking down at, and then I'll be able to find these faces here. So you can see here I'm going to have to find this kind of top surface. So let's find that. Same principles. So on this here I'm going to get 2 points technically. And then I'm going to get another 2 from here. Okay, so somewhere down along there. And what I want to do now is a little bit of sliding set squares once again on the opposite side. Get my 2 points from the top surface over here. And as you can see, probably brought it a little bit far, but just locate my points. That'll be 1. I assume this is number 2, yeah. And 3, and technically, if I wanted to find the other one, it would be back there, but obviously I can't see it. So just heavy in the important stuff then. Okay, so there's our top surface, as you can see it, and now what we have to do is just complete our bottom surface. So same principles just as we did there. I'm going to basically get this face here and this face. So sliding set squares, I'm going to line it up. Just going to project this one a little bit further there, and likewise with this guy over here. This one a little bit further, and what you'll actually see then is from this point to this point and this point, it literally just comes vertically down. So just using my T-square there, I'll project this down. They should match up, and I can see that they do. That'll be a good test of your accuracy. I'm quite happy with all that there. So now it's just a case of having in the information, making it stand out. That there is the first part of the question, part A. So we've completed now the axonometric projection, which was done through diametric in this case. Once again, where I told you that the axonometric plane is 2 angles that are similar. So we can obviously see then that this image we have here is very similar here, so we know we're on the right track. Okay, and as you can see, you don't have to use labels, but I find they'll just help you. Okay, so being able to label over here and understand it as well. Now part B of the question, it says, determine and indicate in degrees the true angle between the surface ABCD and the horizontal plane. Okay, so we know the horizontal plane is essentially the ground, okay? So we need to basically see in which view here can we see the surface ABCD as an edge view, because that is the only way we will be able to tell what angle it is. So if I look over here at this view, I see ABCD. That there is not an edge view. An edge view is one where I would see it as a line. But if I look over here in this view, which is like the side view, okay, or the end elevation, we've got the surface A, B, C, and D. And I can see clearly there that is an edge view. So because that is an edge view, I know the base is sitting on the ground, so I know this here is acting as my horizontal plane. So what I'm actually going to do is very simply there, to just checking your understanding, that you understand your planes of reference. I'm going to extend that out there. And what I'm also going to do is, with a light line here, this time, I say light line just using a different color pen, I'm going to extend that surface down there, and essentially the angle there is basically the angle that they're asking me, the true angle between the surface ABCD and the horizontal plane. So using your protractor, if you have one, what you would determine is that the angle here is actually 55 degrees. Okay, I've previously measured it, so it's okay, but just that angle there, then using your protractor, you would know that that angle there is 55 degrees. So that there is your part B of that question. Okay, hope you found that helpful, guys. What we're going to move on to now is the part, A2 at the bottom of this question, just underneath. Okay. Right, folks, question A2 on this page, it says the image below shows a drawing board and two set squares. The drawing on the right shows the plan and incomplete elevation of a similar drawing board with a 30-60 set square and also a 45 set square. So we can see obviously kind of a real life image here, and what they've given us over here is the orthographic views of it, the elevation and the plan. And we can see that the elevation is incomplete because the drawing board is incomplete, and also there's two set squares down here that need to be drawn in. And then it says part A, complete the elevation of the drawing board and the two set squares. And then part B, a line from point A is drawn on the surface of the board. The line has a true length of 50 millimeters and makes a true angle of 45 degrees with the bottom edge of the drawing board of the board. Draw the projections of this line. Okay, part B, a little bit tricky there. Probably have to work that out in my head myself there in a second. But part A, complete the elevation of the drawing board and two set squares. Okay, so we'll start with that. So first of all, we can actually put in the outline of the drawing board, and we can complete that in heavy because we can see that the two set squares are not overlapping any of the edges, so I can heavy in that straight away. Okay, get some marks for that. Okay, so there's my drawing board complete. Now what I have to do is complete the set squares. So you can see here from my plan view, I've already got the bottom edge of my 30-60 set square here. It is obviously a 60 degree angle, 30 degree angle. Okay, if I was to write them in, you'd obviously see that to be my 30 degrees, and then obviously I got my 60 degrees, and likewise over here 45 and 45 as well. So I'll just write those in. I think they might actually be helpful for the next part. Then obviously we've got our two 90 degree angles here. Okay, you don't have to put those in, but just to give you an idea of where the set squares are and what they are. So we've got the top point up here, and I know that top point connects down to here. So I'm heavy in that straight away. So that's that bit there. Now what I will know and what I will understand is that they've given me this edge here of the inside portion, obviously where the set squares obviously usually have an opening, as you can see here. They've given me this kind of edge there. So what I need to do is I need to find this point up here specifically so I can connect that up there. Okay. And what you can actually see really here is, and what's important to note is, if this is parallel with this, they'll also be parallel in the opposite view as well. So to be able to determine where this point is, you can see here that the line has already been projected up. I'm simply just going to extend that up, and somewhere up along there is going to be my point. So a bit of sliding set squares here now. It's just understanding your lines and what they are parallel with. So I'll extend that up there. You can see there I have it. So find that there now. I can extend that over here as well. You can see then that they turned out parallel as well. So there's our 30-60 degree set square complete in our elevation. Likewise, we have to do the exact same in our plan view. Now what's important to note is that this line here is actually a true length in our plan view, whereas in our elevation it's not a true length, because it's parallel to the principal plane in elevation, therefore it makes it a true length in plan. Okay, likewise with these guys, true length here. Okay, there we have, because it's parallel with the XY line in my elevation, it is a true length in my plan. So I want to find this guy, so you can see then it's simply a case of connecting over there, and to find where he finishes, I have this point, but to find the exact position of where it finishes, project that up there, that'll give me that. So heavy in that edge there now, of my 45 degree set square, just as far as there. Now what I want to do is I want to find the point up here at the top. So to find that point up there at the top, okay, it's up here somewhere, that's already projected up, and I can see that it's going parallel with the edge of the T-square, or of the drawing board. Okay, so if it's parallel here, it's going to be parallel in the other view. So a bit of sliding set squares once again. Make sure that's done correctly. And likewise over here. So there we go, I can connect that up. That there will be my 45 degree set square completed in my elevation. And once again, we also have to find the image of the internal portion of the set square. So check this up. Look here somewhere, likewise with this guy, and then likewise with the top point. Okay, nice little question here. I can see here that parallel with that in my plan is the base of the both set squares here, and the inside parts are also parallel, so they will be actually at the same height as these guys. Check them over, so I can heavy that bit in from there over to here. And now it's a case of finding this point. Okay, and once again, relationships parallel, so a bit of sliding set squares up here, once again parallel. So I just want to make sure you're 100% accurate on it. You should be using pen on the day, or sorry, pencil I should say. So from there, now got that edge. And likewise, if I'm accurate, these should also be parallel. And there. Okay, so there we have our elevation completed of the 36 degree set square and the 45 degree set square. So that's part A done. Now for part B, it says a line from point A is drawn on the surface of the board. So you can see here they've given us A in elevation and plan. Okay, so we can see it's up here, and it's also here in our plan view, but it obviously has a height, as we can see from our elevation. The line has a true length of 50 millimeters and makes a true angle of 45 degrees with the bottom edge of the board. Draw the projections of this line. Okay, now you have to listen to what they're saying here. Okay, I'm just trying to work it out in my head here. I think I have it. So it says here the line has a true length of 50 millimeters and makes a true angle of 45 degrees. So this bit here, it makes a true angle of 45 degrees with the bottom edge of the board. So that's actually the important bit there to understand. So the true angle of 45 degrees with the bottom edge of the board. Okay, that's really important there. So point A, if you look at our plan view, you think, okay, or the elevation, some people might think, oh yeah, I'll just go here at 45 degrees. That's not correct, because at the end of the day we know our board, okay, is obviously tilted up. Okay, it's tilted up off the surface, the XY line or the horizontal plane. So we don't really know that that's actually 45 degrees. Okay, but in our plan view, what we can actually know, we can see down here, and what's actually helpful here is our set square. It says here the true angle of 45 degrees. Okay, so the line has a true length of 50 and makes a true angle of 45 degrees with the bottom edge of the board. Now, you can't simply from A just go 45 degrees like that. If we look, obviously we can see our board is at an angle in relation to our vertical plane. Okay, I'm not sure what angle it is, but it is at an angle to the vertical plane. But what we do have on the board, and we can see what's parallel with the base of the board, is our 45 degree set square. Therefore, if I go parallel to this line from A, I can actually get a line to come and connect with the bottom of the board, which will be actually give me a kind of a point of reference up here. Okay, so that's my first step. I'm going to go parallel from A to my 45 degree set square that I have on the board already. So a little bit tricky. It's just checking your understanding of planes and lines. So just there. From A, I want to go parallel like that to it. Put that in a little bit heavier. Where that hits here, okay, right there, I can now project up to my elevation, because that's a point that's on the XY line, or I should say on the base of my board, and now I can actually find the image of that line in my elevation. Make sure I have the right one yet. I can find the image of that line in my elevation. Now, the issue I have with that line is, even though that line is at 45 degrees, that is my correct line in the positioning of it, it's not a true length exactly just yet. So I can't exactly just come along here now and do the next part of the length of 50 millimeters. I can't just measure down there 50, because I don't know is that exactly 50 millimeters. Okay, so it says it has a true length of 50. This line here, I don't know, because in neither view it is a true length just yet, because in either view that line, the image of that line, is not parallel to the XY line. It needs to be parallel to one plane of reference for it to be a true length in the other. So what we're going to use here actually is the principles of cones. Okay, if I take A as the apex of a cone, okay, so what I'm going to do is, in our plan view, we would see a cone as a circle. So from A, I'm going to do a line like this, and what I'm actually going to do is I'm going to rotate this point here until it hits this line here. And what that actually is doing for me is, by rotating it, I'm rotating it until it is parallel. As you can see there, I just need to extend it out a little bit further. But that distance there, from here to here, okay, I'll call it A to, I'll just call it A to Z in this case. Okay, the distance from A to Z here is the same as the distance from here to here. So this is A to Z as well. I've just rotated it around. Okay, that is just rotated from here to here. Okay, all the way up. Same distance, but what we have done now is that distance from A to Z, I've essentially rotated it, okay, until it hits here, and where I can find that now, okay, by projecting it up to my elevation, okay, which is here. And initially, remember, Z was there, okay, but because that now, this line here, A to Z, is now parallel with my XY line, when I connect that up in my elevation, okay, this line here is the same line, okay, it is the same line, okay, the only difference is that this line is the true length of it, okay, that's very, very important to note. So that there is the true length of the line A to Z, and along that line now I can actually measure out 50 millimeters. There's a little bit of understanding in that, a little bit tricky. I'm going to measure out 50 millimeters right to there. Okay, it's hitting right there, and at that point there, I could also have just measured it out here. Okay, that would have been, sorry, couldn't measure out there. That's the true length of the line. What am I saying? I could have actually, at this point here, sorry, at that point there, brought it down. That's what I should have done. And it's hitting right there. Okay, and at that point there, then I can work backwards by rotating it down to here. And that there now is the projections of a line that is 50 millimeters long, and also at 45 degrees with the bottom edge of my board, right from here to here. To find that in my elevation, simply a case of either projecting that up, and providing I was accurate, okay, it should match up. I could either, because that rotated line there will appear as a parallel line into my XY line in my elevation, and if I'm accurate, they should match up. It's just a case then of, there we go. Okay, so I'm happy with that. It's simply a case then of heavying it in both views. So that one there, the part B of that was a little bit tricky, okay? A little bit in your understanding for that there, guys, but that is how you complete the part B of that. Bit tricky there, okay? So what we're going to move on to now is the part A3, which is at the top right hand of the page. Okay. Right folks, so the next question on this page, question A3, This comes from the topic of conics. It says the image below shows a parabolic bridge at the M50 interchange in Dublin. So you can see here the parabola. Okay. The drawing shows the directrix D1. So we've got the directrix here, D to D1, and the focus F and 2 points P and Q on a similar parabola. So we've got the focus, and we actually have 2 points on the curve as well of our parabolic curve. So it says here, locate the axis and the vertex and draw a portion of the parabolic curve which shall pass through P and Q. And then part B, construct a normal to the curve at point P. Okay, so first of all, we've already got 2 points in the curve, and we actually have the focus and the directrix. So first of all, locating the axis is actually easy enough here, because the axis is always going to be perpendicular to our directrix, and because we have the focus, we can just go straight through. So our axis line is kind of usually a long dash followed by a short dash, long dash, short dash, long dash, short dash. Okay, now through the focus, I'm going to extend the line parallel to my directrix. I'm going to do it like this, my focal line. Okay, and what I want to find now is my vertex. So my vertex is actually found by bisecting the distance between my focus and my directrix. And bisect that distance there. Okay, just need to do one side. At that point right there. And that across. So there we go. Right there now. I've got my vertex, which I put in as V. And the good thing we have here, and we know here, is when we're working with a parabola, what's actually quite helpful here is our line of eccentricity, okay, is based off of 1:1, okay, because the parabolic curve, our line of eccentricity, this guy here, is at 45 degrees, okay, from the directrix. So that angle in there is 45 degrees. So as you can see there, I literally just extended that down. Now, our vertex is also a point on the curve. So what we're actually going to do here now is we are going to find some kind of cut points, okay? So I'm going to pick some various points along my axis, okay? So I'm going to pick some various points along my axis. Point here, which should be in between the distance of V to F, and then I'll pick some further points as I go along. And I'm just looking at the curve here, so maybe one more there. Okay, I can see it comes down to Q down here. So at those, what I'm actually going to do is I'm going to extend all of them up and down. Okay, I might not need that one. To my line of eccentricity. So this a little bit further. Okay, and one more inside the gap. So at this point now, what I want to do is where they all hit my line of eccentricity here, here. That's actually a point on the curve right there as well, where the focus hits the line of eccentricity. Should mark that. This one here, this one, and this one. I'm going to extend all of them to my focal line, this guy here. So in the case where it's inside between V and F, it's going to come down. In this case, these are going to go up. Right there, and finally one right here. And what I do then is I'm going to take that distance from F to where it hits on the focal lines. So here, I'm going to take that distance right there, and I'm going to swing an arc up like that. And that then gives me a point on my parabolic curve. Now, if I wanted, I could do another one. I could find another point in here if I wanted. And likewise with the next one, I'm going to take the distance from here to here. You can see it gives me another point right there. Okay, and while I'm at it then, I should also find it on the opposite side. Okay, so I'll come back here to this guy, mark it out on the opposite side, take the distance for this one, so this guy here, mark him out the opposite side as well. Now I'm going to take the distance for this guy, mark it here, mark it here. Just understanding the steps. Follow this one down, and you can see this one is out here. And finally, the last one, so that's that one there. And don't think I need it as far as it is on this side. So at this point now, you can see my various points on the curve. A point here, 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 here. So from P, I'm not going to extend it because I know I need P for a normal in a minute, so I'm just going to leave that P there. Shade that in as best I can. Into my vortex, on the opposite side. There's a point there, point there, point there, and point there. Okay, heavy that in. Try to make this curve as smooth as possible. A little bit inside it there now. Okay, so there is our parabolic curve found. We've also found the vertex, and we use our focal line and our line of eccentricity. So sometimes I write LOE here, line of eccentricity. The next part now, okay, it says construct a normal to the curve at the point P. Okay, what's actually helpful here is we've already kind of got this line here, and if I connect P to F, generally when teaching this in a class, the teacher would explain about getting a tangent, but we know that a normal and tangent, the difference between them is just the normal is perpendicular to our tangent. So from F, I'm going to connect F to P, and I'm also going to extend this down here a little bit further. Okay, and at this point here, we know if we think of junior source technical graphics in relation of an ellipse, anytime you connected two focal points to a point on the curve and then extended your lines and bisected the angle, just depending on which angle you bisected, you will get a normal and a tangent. So if I wanted a tangent in this case, you can see here my focal point to the point, okay, and I've extended it on. If I was to bisect this angle in here, that would actually give me a tangent to my parabolic curve, okay? Whereas if I bisect this angle inside here, that will give me a normal through point P. So that's what I'm going to do, because that's what they've asked us to do. So from P, I'm going to bisect this angle inside in here. There we have it. And at that point right there, I can now connect that to P, and here I have my normal. Okay, if I was to get my tangent, basically, obviously that would be perpendicular to it. So just to show you that there, this line sets where it's rotated around, and we would have our tangent as well if I had wanted it like that as well. okay, and they will be perpendicular to one another. But that is the question completed there, guys. Hope you found that helpful. Now we're going to move on to the last question at the bottom of the page, A4. Okay, folks, so the final question on this page, it says question A4, the image below shows a fragrance bottle and a diffuser reeds. Okay, so we can see here the fragrance bottle and the little kind of reeds coming out of it, and they're obviously all jutting out at different angles. The given elevation and plan show two similar reeds represented by the lines AB and CD. Okay, so what they're saying is AB is a line that is maybe at an angle kind of like that, and then CD is a line, just trying to see what it looks like. CD is probably a line that's kind of going something like that, maybe. Okay, and there's obviously little gaps in between them. Okay, and that's what we're seeing. We're seeing obviously the elevation of the plan. So the elevation of that is up there. CD is kind of like that. Okay, so we're getting little gaps between them. There's the elevation plan of two lines. Now, it also says determine the projections of the shortest horizontal distance between the lines. So what we're trying to do is we're trying to find the shortest horizontal distance between the lines. So we need to be able to basically get a true length down here in our plan view and see one of these lines kind of as an edge view, okay, or the true length of the line. So what we're going to do is we're actually going to create a plane up here. This is Skew Lines, okay, and it's something you should have learnt in class. So to be able to see the shortest horizontal distance, what we're going to do is we're going to use one of the lines up here, and we're going to go parallel to that off of another one. So just looking at it here, I could go parallel to the line AB from C. I'm just looking at that, and I would have to go all the way out here like that. That's probably bringing it out too far. I'm actually going to go parallel to the line CD, and I'm going to do it. I could come down from B, yeah, that would work, or I could go up from A, just come down here. So I'm actually going to go parallel to the line CD. So a bit of sliding Z squares, parallel to the line CD. I could go from B. Okay. I might go from A, actually, just keep it neat and tidy. Just looking at the other question, part of the question. So from A, I'm going parallel to the line CD. Okay, and using my T-square, I'm going to do a level line from B across, and I'm now going to call this point here ABCD, so I'm going to call it E. Okay, so I found a point E there, and if we think back to mining geometry or road geometry, what we've found here is kind of like our strike line in our elevation. And what's important about the line BE is that it is parallel to the XY line. Therefore, once I find E down here and I connect it up to B, that will actually be a true length in my plan view. So to be able to find the point E, well, first of all, I know E has to be somewhere directly below it from my elevation, so it's somewhere down along here. I'm not sure exactly how far I have to extend it yet, but we follow the same method at that point then. So the line CD, I'm going to go parallel to that. So parallel, the line CD, parallel, and I did it last time from A, so I do the exact same thing. Parallel to the line CD from A, and you can see there where it's after cutting, that is now after giving me my point E in plan. And I'm going to connect that up to B. And that there, when I connect it up to B, just trying to be as accurate as I possibly can, I'm using pens here, that line right there is actually a true length, because BE here, BE in elevation, is parallel to a principal plane, okay, it is parallel to the horizontal plane, therefore making it a true length in my plan view. So I'm going to write that in there. TL stands for true length. Now what we're going to do is we're going to look along that true length there, the line BE, and we're going to set up an X1, Y1, and that will actually give me an edge view of my plane AEB. Okay, so looking along that there, I'm going to extend that out. I'm going to rotate my set square, and I'm going to set up an X1, Y1. That looks long enough. Okay, so that's my X1, Y1. Now what I'm going to do is just make sure I'm set up properly there. There's my X1, Y1. I'm going to project out perpendicular to that for all my points. So if I want to find A, C is on the ground, it's actually touching the XY line, so C only comes to there. E and B, this one I have to go a little bit off now, so make sure I've done that correctly. Yeah, sorry about that, my accuracy is just a little bit out. What the hell am I doing there? My accuracy has just gone a little bit out there, guys, sorry about that. I'm just going to fix this up here. Whatever way I must have moved the set square slightly. So I'm actually going to bring it out a little bit further. Just bring it out. Yeah, there we go, I did it again. So there is my correct x1, y1. Yep, that's better. That's better. Sorry for that. So there we go. C is out here. B and E will be out here somewhere. And then finally, if I wanted to find D, likewise. So D will be out there. So anytime you project from the plan, normal orthographic projection, okay, we're taking an auxiliary view here. Project from the plan, you're going to take your heights from the elevation. So I know C is already on the ground, so I know this line is in the way there, so apologies for that. Just scribble out that there. Obviously use a rubber on today. This point right here is going to be called my C1, and I want to find now. So A, I want to be able to find him. So I'm just going to connect them up. And B will connect up to B there. I'm only doing this so I can get the exact perpendicular heights. And using my compass, I'm going to take the height for A. Come down to A, follow it out to my x1, y1, the correct one in this case. There will be A1. I'm going to find B. I'm going to find B1. And likewise with D, it's actually coming up the same height. So it's D1. And E would have been out there because it was the same height as B. There we go. So technically what I've actually got here now, let's write this in. So this is A1, this will be B1, E1, then I've got D1. And what we should actually find is that these lines should be parallel. Now this all comes down to my accuracy, and I am using pens, so hopefully I'll just check that they're parallel. Yeah, I'm actually happy with that. They came out okay. So that line there is parallel with that. So now we can see that they're parallel. So what we want to actually do now is we want to get the the shortest horizontal distance between them. So the only way I can actually see that is where I find kind of like the intersection point of that, okay? So I'm going to set up now an x2, y2 perpendicular to my x1, y1. So perpendicular to my x1, y1, I am going to get set up an x2, y2. I'll write it in there with a nicer pen. x2, y2. And because I set it up perpendicular, I'm going to project up also perpendicular. So if I wanted to find A will be up there somewhere. Likewise with D and D. So using my compass, now we've done an x2, y2, we're going to take the distances from our last xy line back. So x2, y2, our last one is our x1, y1. So if I wanted to find B, put that in a little bit shorter there, right? So if I wanted to find B, So it's that distance right there. Make sure I have it exactly. Yep. And I'll come out to B here. I'm going to mark B there. That'll give me B2. I'm going to do the same for C. And C is along this line. That'll give me C2. Same for A. A is up here. And then finally the exact same for D. It's a little bit shorter. And D will be up here. So label those. D2, C2, I've got A2 and B2. Okay, so in connecting those up, what I've actually found now is it's like I'm looking down on top of them and I'm actually going to see where they intersect here. That is actually showing me the shortest horizontal distance between them, or shortest horizontal line I should say. So projecting that back, there's a little bit of work in this. I'll project that back, and find that here. So there's the shortest horizontal line. So I'm going to go SHL and project that back in all my views. So that was it in the X1, Y1 view. So this is where it hits the line AB, so it's right there. And find where it hits on the line CD. So that's where there's getting caught in the page. Connect those up. SHL, and finally, if I have them in my plan, just find them in my elevation. And hopefully it should be a horizontal line. And you can see that they're matching up and it should be parallel with the XY line. Okay, so that there is the part A, guys. Determine the projections of the shortest horizontal line between the skew lines. Okay, so SHL, shortest horizontal line or shortest horizontal distance almost. Okay, part B, determine the true length of the line joining A to C. Determine the true length of a line joining A to C. So part B, I'm going to connect up A to C here in both my elevation and my plan. Okay, determine the true length of a line joining A to C. So this is easy enough. It's simply a case of, you can do it in either view, but based on the space that we have, I'm going to do it down here. I'm going to set up an auxiliary view parallel to my AC and my plan view. Okay, and then take my distances from the elevation. And that will give me the true length of a line joining A to C. So it's a nice and easy one here. So I'm trying to keep it neat and tidy because I know I messed up here a while ago, so apologies for that. X1, Y1, and having done a parallel auxiliary view, I'm now going to project out perpendicular. So the good thing is here I know C is touching the ground. So C is right there. A will be out a little bit further. We're always projecting out perpendicular to an auxiliary view. So my A then, I simply take the height from the elevation, that height right there, come out to A here, mark it out in my plan, on my auxiliary view. Once again, this is A1, and what I have actually found here by connecting it to C1 is the true length of a line connecting A to C. So that part there was quite easy. Okay, a little bit harder over here. Okay, so that there, guys, is the question A4 on the 2020 section A section. Okay, hope you found those questions helpful. That is then complete. Okay.